Right. So it was a bit of a surprise to get asked to give this talk, and a great honor to be chatting to all of you folks. So I went to industry just over a decade ago, and it was a surprise. I had to go for various reasons, because some of my colleagues told a startup to Meta, is why I had to go. Now, at that time, I was an admirer of abstract interpretation from afar, right? I was a theorist. I loved this lovely theory. Now, the funny thing happened is that when I went over to industry, I found that I liked it a lot more. And I want to explain why I liked it a lot more. And this is a bit of a jokey title. It has all to do with trying to deploy program analysis to people. And me as a person trying to help make program analysis. Now, the first thing that made me like it was like it more. I already liked it as a theorist, right? So after working at Meta for a while, back then it was called Facebook, that's right, I took upon the task of building a program analyzer. Now, Infer had gone into Facebook as a program analyzer based on separation logic. There's still lots of separation logic in it, but at some point, one of the engineers, Sam Blackshear, made an abstract interpretation framework inside of Infer. And so now Infer has a whole bunch of little abstract interpreters inside of it. And my task was to make a new program analyzer, and this was much easier because of that, right? Like, it had the join, it had the widening, it had lots of little abstract domains to play with. It was much easier for the analysis designer to set this up because the primitives had been discovered, and the primitives were right. So, in a sense, it was a good piece of software engineering, abstract interpretation. They made the analysis designer's task easier. Now, although we set it up using the abstract interpretation theory, so to speak. Oh, one thing we discovered as a result of this is abstract interpretation, by you folks, wasn't thought to have been finished in 1977, right? Like, there were subsequent papers, and in particular, Cousteau and Cousteau wrote many papers updating abstract interpretation along the way. For me, this made me calmer, because it's like a living subject, and it's okay to change the primitives. And in fact, we used the ideas from one paper, Abstract Interpretation Frameworks from 1994, was the one that had the right primitives that we used to set up the abstract interpreter. But we did some bad things too, right? So we implemented operations in the abstract interpreter, but they didn't satisfy the axioms that they're supposed to satisfy, right? And so we're not going to do much math in this talk, but some of the stuff that they did. Oh, I'm going to be telling a story about what I learned at Facebook, and there's later on we'll tell a story about a bit more that I've learned after Facebook, and it's all in this paper, CACM paper, and one of the authors is here, I think, and he'll catch me if I say anything wrong about his part of the work, I'm sure. But before we get started, just to keep you all calm, we'll have 2 slides of lattices, okay? And then no more lattices. And so then, I mean, we've got a transition system, and from the transition system you can get a predicate transformer. And y'all are smart enough to use backwards analysis to work out what it means to be a transition system here at the top. And given various things, you can state what it means to be an invariant in Floyd's sense, just in the lattice terms, that it's a superset of the least fixed point. And then if you find a superset of the least fixed point which is less than something you're trying to prove, then that's sufficient to prove it, right? This is how abstract interpretation works. And the interesting thing down there at the bottom is if you find something that's not less than what you're trying to prove, that doesn't disprove it, because that just means there's possible false alarms. And then part of the badness that we ended up getting into is let's say that instead of invariants, we talk about subvariants. And so x is less than the least fixed point. And so this is under approximation now, right? So I made this gadget called incorrectness logic a few years ago, and it's basically about this. And if the least fixed point is not less than x, then x is not an invariant. This gives us a way to disprove programs, is what it does. And what's very interesting is that the under approximation theory is not exactly the dual of the over approximation theory, because the dual of the over approximation theory is in terms of greatest fixed points, not least fixed points. But in any case, So we ended up doing some badness there. So I just wanted to keep you all calm before we leave abstract interpretation. And so in particular, if you've got an under approximate semantics F under bar and an over approximate semantics, then you can see things like the kind of badness we were doing is we were stopping unrolling while loops after n steps and saying we're done, right? And so if you do this in over approximation land, this is very bad, right? This is not sound, but in under approximation land, it's sound. So this is the kind of thing in our widening operator, we were doing things like that. So we'll get into sort of why we were doing things like that, but okay. Now I want to tell the story, a bit of the story of Infer at Facebook and what we learned from it. So we joined Facebook, a little startup company, but got bought by Facebook, and then we went into Facebook, and then we were started to bump into this question of scale. So these are numbers from around 2013, 2014. There are many commits per week, right? There was 100,000 commits per week, say. So if you've got a long-running program analysis, what are you going to do with 100,000 commits? It's going to be very difficult, right? So it turns out that we had an incremental program analysis, right? And so the incremental program analysis could run just on the code changes, and it could run really fast. Infer, because it was incremental, we used the word compositional. We derived the compositionality from separation logic. Because it was incremental, no problem dealing with these 100,000 commits in terms of scale. And so it would run on the code changes in the continuous integration system, and it would report any new bugs that it found on the code changes. It wouldn't report any old bugs. And it fit with the developer workflow like this. And so the scale wasn't a problem. The incrementality was very important. Right, so it did stuff like that. And it participated in the code review process. I'm just waiting for this to go. Okay. I might have. Oh, okay. And so then it would write comments on the code review system on pull requests. Facebook has, of course, they don't have they have all of their own internal stuff, but it mirrors what's external. Now, something was really shocking happened after we deployed this. The first thing we did before we deployed that analyzer that way, we deployed it in a batch mode. We found a bunch of bugs. We made a list of bugs, and we showed the bugs to the people. Now, before this, we did what all good abstract interpretation people or program analysis people should do. We got the analysis to the point where we thought that the false positive rate for what we were reporting, which was resource errors, was quite low. We thought maybe it was 70% true positives, maybe 75%, something like that. But we thought that it was giving good signal, and then all of a sudden, 0% fix rate. We shipped the bugs to people. People completely ignored them. So they didn't care. This was the problem. And so I had many sleepless nights at this point. I thought, like, we've just sold this company to Facebook. We just brought this tech that I love. We've deployed the tech to the people. The people absolutely don't care. What am I going to have to do? Maybe I was facing, like, going back to academia with my tail between my legs as a complete failure at that point, right? Like, this was very, 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 very scary. Then we switched on this other mode, in the workflow mode. And in the workflow, we didn't expect this, but the numbers came back. First, we thought it was over 80%. Then we found out it was 70. It was very high fix rate. This was for the exact same program analysis, where whatever the false positive rate was, it was the exact same false positive rate. And so, why would this be? Why, like, I've heard things like, it's important to put things in the developer workflow. Nobody ever told me 70% versus 0%. Nobody said, and so I was basically shocked by this. So, you see, I was treating the industry, the software engineering, like a scientist does the natural world. Like, we see these things, and the engineers surprise us, and then we say, oh my God, how am I going to understand that now, right? And so this was one of these things like, oh my God, how am I going to understand this now? Why is this workflow? There's a better reason, which was very interesting. And the engineers were saying things to me like, oh, it's amazingly fast and a way better experience. The speed mattered a lot, but the most important thing was, they said, losing context. So I can explain why this one deployment mode was so much more effective than the other deployment mode. So it's got to do with the mental cost of context switch. Now, suppose you're doing a mathematical proof, right? And suppose somebody says, I think I found a bug in your paper from 10 years ago. Then you need to swap out the mental context of this proof you're doing, go back to that proof, swap that back in, which is going to be pretty difficult, answer them, then come back, then swap back in. That's a very expensive operation, right? When a software engineer is working, and then we say there's a bug, and they have to completely swap out of the context, it's very expensive for them. They don't want to leave their workflow. If we report in this way, we're reporting bugs when they're trying to land the code. It's absolutely in the workflow. It's really, and so how much of a difference this is, in this case, was 70 to 0, right? And so the consequence of this is many of the program analyses, even dynamic at Facebook as a consequence of this experience, tried to go for this mode of deployment. So speed matters, incrementality matters, learned amazing things from the people. And so this made me think of something that I had never thought of unless I bumped up against the people in the industry. So false positive rate, we are taught that this is very important. I wonder if people who haven't heard this before can tell me things that are wrong with the concept of false positive rate. Maybe they can't. Maybe we won't run this like an undergraduate lecture or something, right? I'll say it like this. I say, it's good for a measure to be measurable. In an engineering context, the false positive rate is not measurable, right? Something that's measurable is performance. I can measure that as it's in prod. The percentage of time that the analysis crashes, I can measure that. I can't measure the false positive rate. It needs humans in the loop, right, to make guesses about what false positive rate is a great theoretical concept. It's not measurable. It's less useful in an engineering context. You need to measure things when you deploy real software, or else it's going to go wrong and you're not going to know why it goes wrong. On the other hand, fixed rate is a measurable concept. I can measure the rate at which my analyzer warnings disappear as a consequence of diffs. Furthermore, fixed rate speaks to do they care, right? Because if they fix it, they care. If they don't fix it, they don't care. So it's not the same as false positive rate. False positive rate is a good concept, but it has lots of limitations. Fixed rate is something I can measure. It's much more useful. Yes?
Question.
Yeah.
That's not enough, no? You also need a countermeasure. So
no, it's not enough. There's more than just this.
Yeah, you need a countermeasure because you can increase the fixed rate by a lot by introducing a lot of false negatives. So you need a countermeasure.
Yeah, I'm not saying that these are the only measures. You have to track bug volume, which is a partial countermeasure. But I'm not claiming I have all of the measures one would want, but we track bug volume as well as fixed rate. Like if you get a very small bug volume by looking at more short errors, then your fixed rate will shoot up.
Okay, we can take it.
That's right.
But it's
But,
not enough because you also need a recall measurement.
Yes. So I know what he's talking about, and we can get into that. But it was just very interesting to me to bump into the people and to see this. Now, the fixed rate is impacted by a number of things, but by the false positive rate, whatever it is, also by the speed of the analysis and when it's deployed. This was very, very interesting to me. So what Facebook liked about Infer, first of all, they liked that it scaled to millions of lines of code, not just thousands of lines of code. They liked that it was incremental, so we didn't have to have the bug list deployment. They loved that it found bugs, right? So they loved that it found lots and lots of bugs. So if we explained to the VP what's the impact of Infer, it would have been like, well, for this last 6 months, some large number of thousands of bugs were fixed, right? That was one of the things. There were other things that it did, so they liked that. What they never said, the VPs never said, was it proved the absence of bugs. They never gave that as a reason for why they were happy, even though we tried to sell that to them. We tried to explain again and again, this is what it does, isn't it interesting? Never did they pay attention to that. And because of all of this, it's because of a lot of this experience that I ended up working on incorrect under approximation. Jules and others made under approximate compositional interprocedural program analyses, which were symbolic, and those were very effective. So I never would have ended up working on the bit at the bottom which became incorrect as logic, without trying to deploy this. Other people might have, but without trying to deploy this to the people. So it was very valuable for me personally going into the company, trying to do stuff, and then the gift back is I had to change my attitudes about program analysis. Now, on to the next bit. Zonkalan at Facebook. I've never explained how important this was to me, and so I will explain this now. So it works for this thing Hack, which is PHP, a typed version of PHP. And the story of Hack is very cool because an OCaml programmer who really knew types went into FB and said, "Oh my God, we need types." And he took all of the OCaml notions and he put them on top of PHP. His name is Julien Verligue, which is an amazing programmer. And then he charmed or explained to the engineering population of untyped programmers how types would be great, and he won that argument. And now it's a typed company, and it's really astonishing that happened. So anyhow, there's lots and lots and lots of this code. So Zonkalan, which is Francesco and colleagues, made a program analysis which was going after taint errors, right? So these taint errors, I hope I remember to say something about this on the impact slide. Going after taint errors. The security team and the abstract interpretation team worked together to make this. This scales like you wouldn't believe, right?
Actually, the number is larger.
Yeah, I copied this from the paper.
There is an S under Windows Docs. There was an S after. We couldn't give the real number.
Yeah.
But it's more than 100.
Yeah, and it must be over. I can say it must be, since I'm not in the company. It must be over 500 million locks now, right? Like this is real scale. And so sometimes it commented on pull requests, but the majority of the impact was what I would call batch mode. Give a bug of lists to somebody, and then it works. Let me explain something more about this. So, did I get the impact of? Oh, okay. So Facebook liked about Zonkalan is it scaled to millions of lines of code. In contrast to what I said about Infer, it had few false negatives. So it was engineered to be an over-approximate abstract interpreter. The extent to which it was exactly that, I don't know. But for instance, they didn't stop after 3 or 5 iterations for the fixed point. Boom, they went for the fixed point, right? So they tried to go all the way. So they were trying to be over-approximate. Infer landed at Facebook, was trying to be over-approximate, but pivoted to under. So that was quite interesting. So a gift to me was an appreciation of when over-approximation is really good, and I'll explain that in a second. So what it was searching for was these taint analysis errors. So I won't explain this one in detail, but this says attacker can delete a user account by puts an input on line 5 that causes a redirection to any other form on Facebook at line 20. And so the taint analysis follows these kinds of things. These kinds of bugs, like Infer was trying to find race conditions, it was trying to find null pointer exceptions, memory leaks, other things. This is trying to find these taint errors. These taint errors aren't necessarily so hard from the analyzer perspective. From the human perspective, they're very difficult. Let me explain an example why they're difficult. So Infer had a taint analyzer too, because we copied Zonkalan ideas at one point for a different programming language. We found a taint error in some Google code. There's this thing called Garrett from Google. And so we found a taint error that looked very bad. And so then our engineers looked at that taint error, the Infer engineers, and they said, is this a false positive or a true positive? 10 hours later, didn't know. So then the engineers ring up the Facebook security engineers, absolute experts on for the team Francesco was working with. They spend 10 hours or so on this one taint warning. Is it a true false positive or a false positive? Don't know after 10 hours. Like, tell me about measuring false positives rates. The absolute world experts can't work it out in 20 hours for one bug. So then we contact Google. Google, is this a true positive or false positive? Googlers never answered that question. They just fixed the bug, right? So that was a very entertaining situation. So Zonkalan impact was this, which is, the impact was more since then I've heard, but in the 2 years to 2019, I found over 40% of the serious security issues, let's call them SEVs, inside Facebook, and I found thousands of such. It found more than the bug bounty program found. It found more than the internal reviews. Oh, we didn't even mention fuzzing here, right? Like, Facebook had an internal fuzzing team, right? That were working really hard to deploy fuzzing at Facebook. So they weren't mentioned. I presume they found less than any of these three things. But I remember some stats because I really like fuzzing, right? Like, okay, I'll tell the story like this. Like, when I landed at Facebook, I wanted to do what Francesco and them did, right? I wanted to do taint analysis, and I remember asking all kinds of people, does taint analysis actually work? That means, does it actually find important bugs? I went through paper after paper after paper, didn't find any important bugs reported from taint analysis in the literature. And I said, oh, I'm a bit doubtful. But then, at that time, fuzzing, finding lots of important bugs in the literature, right? Good. But then, what I learned from Zoncolan is that it works, and it works really, really well when done by the correct people. So we had an internal fuzzing team, and the internal fuzzing team was trying to deploy fuzzing at Facebook. Now, fuzzing ended up covering, at that point, I think like 3% of the code or 2% of the code of the company. The great difficulty with fuzzing is I need to set up the fuzz harness, and then I need to get the fuzzer to go. That takes an enormous amount of human time. Enormous. And by the way, if you write a bad fuzzing harness, you do get false positives, right? So it's a hugely labor-intensive process. So static analysis, on the other hand, covers 95 or 98 or 100% of the code at Facebook, right? The kind of static analysis we have, the compositional begin anywhere ones, can start from anywhere in the code. Not a problem. Start it from any point and go. There's problems. Nothing's perfect. There's problems, but the deployability of static analysis is light years above the deployability of fuzzing, and this makes a difference. So fuzzing, when you can deploy it, it's good. Very hard to deploy. Oh, so what I learned, though, this was, so yeah, it meant a lot to me. I don't think I ever said something so positive about Zoncolan and Francesco's presence, but it meant a lot to me because it changed my mind about taint analysis. It showed me a case where over-approximation, even at scale, works really, really well. And it made me understand fuzzing, taint, security, all that a lot better. So, but then there's a question like, Zoncolan was over, Infer was under-approximate. I mean, modulo means modulo some assumptions, right? But they're engineered to be such, designed to be such. They both had quite a bit of impact. Infer had a very, very bad time with batch mode, right? And a great time with the incremental deployment. Zoncolan had great success with batch mode. Why would that be? I mean, oh, that's very interesting, right? And the reason is the people that it's deployed to. And so Infer targeted, in the first instance, it could target the second group, but in the first instance, it's going after developers. And so there's very many developers, right? In that company, very many thousands. And so what's the job of a developer? Let's ship features. What did they say to the program analyzer? Don't slow me down. Don't give me false positives. They're very upset. On the other hand, Zoncolan was shipped to the much smaller community of security engineers. Their job is the security of the entire code base. They have all of the context. They do want to go through a list of bugs and get rid of issues. They really care if there's false negatives. So the security engineer's job is, let's find SEVs. They're not saying, don't slow us down. They're saying, whoa, be careful. And they're saying, yes, dashboards, they do. So it's not for all. You know, nobody wants false positives. Nobody wants false negatives, right? But the people that these things were deployed to had a big impact on the deployment model and what would work for the engineers. Okay, so that was, I would have known nothing of this if I hadn't tried to deploy this inside the company. So yeah, no false positives. Right. Okay, so that was good. So that stuff I actually learned, and this talk is supposed to be in a session about the future of abstract interpretation. I don't want to be so presumptuous as to tell people about the future. I'm in the middle right now of what happened at Facebook. What happened at Facebook was I went in, tried to do a bunch of things, finally realized some stuff that I've just told you some of it, right? And it took ages to realize that, and a lot of hard work. So I'm in the middle of that again now. So I haven't realized everything yet. I'm in the middle of it. But I thought maybe it's more fun to just tell you some of the in the middle instead of the only after the fact. So I'm just going to tell you some of the in the middle bits now. So I had worked for Facebook for 8 years, and then sometimes you need a change, right? So I decided to have a change, and so then I went to this company, Lacework, which is a cybersecurity company. And what I wanted to do, I wanted to take the same. This is the first approximation of the aim: is take the experience of static analysis at Facebook, ship that to every company in the world. That would be awesome if we could do that, right? Like that's the beginning aim. Then that's not actually possible because not every company has the budget and everything else that Facebook has. But that was the aim. I said, I don't want this to only be for certain expensive companies, right? I would like to ship that. And so the kind of idea we have is that what Lacework has is there's many cybersecurity companies out there that are basically program analysis companies now. And what Lacework has is it has dynamic analysis on the right. These are the things called agent and agentless scanning, and I'll tell you a little bit about it. And then there's static analysis on the left. And our aim, and we're doing a bit of it, is to have them talking a lot. And so I'll just explain by example a bit of this. And so we'll start with the static. And so we only shipped some products a few weeks ago. One of the products is a Zonko-like product, Zonkoland-like product. But here's one of the things it does. So it finds a known bug, right? A known vulnerability. So there's this CVE, which it's an exploitable CVE. The person introduces it into their code. Our tool comments on the pull request and says, you're introducing this really bad bug. Maybe you should care about it. But the interesting thing it does is it gives two additional bits of information. One of the first things a security engineer will ask, if you say you've got a vulnerability in your code, because you've got a lot, or you've got a lot amongst your dependencies, they'll say, is it internet facing? So can somebody get at it right away? We say it's internet facing. Static can't tell that, by the way. We say it's internet facing, and may active means this vulnerability is being used in production. Doesn't mean it's being exploited, but it's being used in production. So these are two questions the engineer will ask right away. And so this is a simple thing we're doing, combining dynamic and static. So static finds the problem, dynamic gives extra context. And the extra context here is more along the lines of, should I care and should I fix it? So internet facing means you should care a lot more than if it's not internet facing. And so the kind of program analysis that we're building is quite interesting. Here's some things that I hadn't worked out before. So we're making a static analysis for first party, so for 0 days, and for third party vulns and some other things. But it breaks into two kinds. There's the buildful analysis, which means we work with build artifacts. We can do a deep program analysis like Zonkoland. Then there's these other ones called the buildless analyses. So they need to be able to scan the code without knowing how to build the code. You might do this in the IDE. And so I hadn't encountered many of these analyses except for linters first. And so then there's a number of deployments via CI/CD. My thought going into the company was, if I want to ship the whole experience to all of the companies, then I do it via CI/CD like we did at Meta, right? Like via CI/CD system. But there's this other thing that I'll explain in a minute, which has certain advantages, which is very, very, very interesting. Now, we always talk about scale. So I'm interested in this problem. Scaling not in terms of lines of code, but in terms of numbers of repos you cover and numbers of companies you can get to. And so a situation I might bump into is, oh, here's a prospective customer, and they come to us and say, I've got 1,000 repos, and I don't have CI/CD hooked up. And then they say, come in and help us with code security. And so now, it's going to be a lot of effort to hook up these 1,000 repos. And so 5 other customers are saying the same thing. And so there's this thing, CodeSec bot. There are these bots, and they're very entertaining. What they do is they hook up to Git, right? And now there's a whole bunch of Git repos that the company has. And what they do is they look at all of the events coming out of Git, or it could be Bitbucket, but all the events coming out of Git, which says like pull request, commit, all these things. And every time it sees one of them, it does a clone, clones it into a cloud, runs the analysis, then sends the information to the customer. The amazing thing about this is that to do that, you don't need the customer to have already set up a CI/CD system. It's almost as if you're automating all of the DevOps for them. But the downside of it is, if that's what you don't know how to build. There's too many varied ways to build the programs. You know this. You download a Git repo, build the program. It'll take you a while to learn how to build it. I can't do it automatically for all the Git repos. But if I do this, then I can scale to loads and loads and loads of code bases and loads of companies. And so what's very interesting about this is that the power of this kind of scaling is like let's think of why are Facebook and Google valuable companies? Well, one of the reasons is because they can acquire new users for very low cost, very easy onboarding. So low cost for the user to sign up, but also the engineering team doesn't need to expand massively every time there's a new user, right? This is when they talk about scale in tech companies, they don't mean lines of code, they mean this in terms of people or in terms of customers. And so this model is very scalable in those terms. Now, it may be that the buildless analysis finds less bugs than the buildful one does, but if I find a few injections per million lines of code, and I do this for many companies, then maybe I'll find more bugs in aggregate for humanity than if I just did it in a deeper analysis for one company. Anyhow, so what's very interesting to me and what we're working on is what kind of program analyses fit this kind of weird buildless situation. Oh, I don't know if you share my sort of delight in seeing weird buildless things deployed in this way to many people. I find delight in it because I know it'll get to many people, but also we've got a new balancing act in program analysis to play. So, second one I want to talk about is this thing agentless. So agentless, yeah.
How do you get feedback from the people that use your tool? So you have also a channel?
We have you have stuff like that, ways to talk to the customers, and you have to gather telemetry and things like that. It's early. The channels and all of that. The product as a whole has channels like that set up. Yes. Posture management is this very interesting thing. Let me see how quickly I can get through this. So, what this does is a cloud system. It's evolving. At any point in time, you can take a snapshot. So that means I can take one state. Right? What these things do is they take a state and then they create a graph from the state. The graph is supposed to represent the risk, where you might come under attack. This is better done with an example. And the example, this is something called an attack path. And the attack path says I can go from the internet to this thing called a Kubernetes service, which has a vulnerability on it, and then I can get to a database. And this is the crown jewels. And this represents the following idea. It says, I can get from the internet to this Kubernetes service, and then, well, if I can exploit that vuln, then I can start performing reconnaissance. And I can look around and maybe find the right procedure calls and whatnot to get to the database and get the crown jewels. What's very interesting is this graph is constructed from dynamic analysis. Point one. Point two, it doesn't represent a real bug. It represents a maybe bug, right? So if you think about it, dynamic analysis together with creating the graph is being used for risk prevention, right? It's not being used for bug catching. And we have various ways to try to get rid of the bug, and one of the and so we try to establish things that are called security invariants. And so there are 3 different ways to get rid of the bug here, or get rid of the potential bug here. One might be the service has no critical OSS vulns, so you would fix this by updating the vulns, and then you can check it again and again. So there's invariants, like in program verification, but they're very easy to check and very intentional. And so what I would just summarize, and I'll have to skip 1 or 2 of the steps here, given the timing, is that what's happening, the way people are working with this, is step 1. computer grabs a snapshot. That's called agentless workload scanning. Step 2, computer creates a graph. That's an over-approximation or an abstract interpretation. That over-approximation or abstract interpretation, like we talk about going over, under, it's automatically usually. That step, computer creates graph, is mostly intended for the human. The human looks at the graph and tries to say, where are the risky bits, right? And they have ways to query it, but the humans look at the graph and try to figure out where should I put my attention to make my system more secure. Then forget that I won't have time to talk about code-aware agent. Then human chooses a path, establishes a security invariant, which establishes an over-approximation going into the future, and then the computer checks the invariant. So the interesting thing to me here is that under and over are happening, but under and over are working together in a way which for me was surprising. So they're being used for prevention, bug prevention. Dynamic is being used to help with that, not bug catching. And human is totally in the loop. The abstraction is created for the human, not for the computer here. So that was quite interesting. I think in the interest of time, there's another kind of abstraction that's going on. But I think what I just wanted to do is summarize what I'm seeing in Lacework. I haven't come to a lot of conclusions yet about this new work I'm doing, but I'm quite interested in it because it's got new challenges. First, scaling to new customers is a central challenge, right? And so not just scaling in terms of lines of code. And we use in prod, maybe I'll use some more academic words. Maybe in prod is okay. There's testing time dynamic analysis, which is what mostly people think about, especially in the scientific community, right? In prod means we're monitoring stuff as it's running, really, the real workloads. And so what I found out, and which is obvious in retrospect, is that in prod it's way easier to deploy in prod to many companies and many people than it is testing time. The reason for that is because the testing setups in all of the companies are so varied, but their in prod runtimes are similar. And so we can make somewhat automated ways to attach to in prod and get results, get dynamic analysis results. Whereas if we were to try to do it for 1,000 companies for testing time, it's very difficult. So even consider this problem, I'm not meaning to bang on about fuzzing, there's other kinds of dynamic analysis. Consider the problem of deploying dynamic analysis to 1,000 companies. It's very difficult because they don't have the same testing setup, but they have this very similar because of the cloud in-prod setups. The other thing people actually like is that in-prod is more true positive than testing time, right? Like, because you'll end up with workloads at testing time that wouldn't be real. So people like in-prod. The other thing that's very interesting to me is this build list versus buildable static analysis. And I'm seeing, not necessarily creating, just observing what people are doing, lots of static and dynamic togetherness. So compute a snapshot generate a graph. There's another thing called workload scanning where they take a history, a 30-day history, generate a graph which is used for anomaly detection. And so this is like putting a lock on your window. This is like a burglar alarm. Both the lock on the window and the burglar alarm are done by combination of dynamic and over approximation. Then there's other dynamic and static that's going on. And so all of this that I'm saying, that I'm observing, so the interesting static and dynamic togetherness, plus having to nail the scale challenge, it's not just my company. There's quite a fair number of cybersecurity companies growing up where they share these or some subset of these characteristics. Okay, that's basically what I wanted to say. Going forward, I'd agree with Mouley's point about when we make the analysis, thinking who we're making it for makes a huge difference. That makes a huge difference for the kind of analyses you create. I think abstract interpretation has already had a lot of impact. Inside Meta, we had at least 5 teams working on it with abstract interpretation experts embedded with those teams. It had a lot of impact in that company anyhow. Maybe I'm becoming like these people who see abstraction behind every tree, right? Maybe that's happened to me. It might have happened to somebody before. But I reckon So I care much more about the spirit of abstract interpretation than the letter. The spirit is very important, and it impacts my thinking, and it's happening, and the spirit will certainly have much more impact. Okay, thank you.
Thank you very much, Mouli.
Yes, thank you for inspiring talk. So two thoughts. I mean, you are obviously right about the fixed rate. We also measure it this way. But if people agree to write specification, then in fact you do have, we in Satora, once the person write the spec, they know what's a false alarm. So if people, maybe in your domain it's not realistic, but in domain that people care and they are willing to write what's right, then in fact you can, so maybe that's not in your domain because people in this domain, they don't want to say what they expect. That's what you're saying. So basically that's maybe a question for you. Do you want people, you think there's no way, maybe that's an idealistic question, not? Do you think there is a world where people will want to write in their code or just their code? Is that your feeling that?
Right now, there are two groups of people we're serving. Number one is the security engineers, and they need to know a lot about what's happening, and they do care about the analog of specs. And if I can get excuses to verify little bits of code, I will take that excuse, right? So there's a small community of people who care about little bits of things that have totally got to work. Then there's the security engineers, that's more. Then there's the developers. All of the developers, I don't think we should think about trying to convert them. Right? They've got to make features, so I don't think they're going to be writing specs. That's going to slow the majority of them. I don't think we should think about this. So the way I approach it is I want all these reasoning techniques to help everybody, right? And so, okay, over approximation for security engineers, great. Full-blown program verification for people, great. I want to meet these people where they are. Under approximation for all of the developers, great. I want to help all of them. And what I really learned this at Facebook, it's important for the experts to meet the people where they are. We can chase them at what they're doing a bit, but to me, not make them come to us. We have to go to them. And there's another nice slogan. We don't want people to help abstract interpretation. We want abstract interpretation to help people. Right, so I think we're on the same page, but that's my answer.
So the second is more a warning to you, because I think you are saying something right, but you are saying that in prod is easier. But the problem is in prod in many domains, including us, is that you're ignoring the most important thing is mitigation. Once the bug is there, the question is how do you fix it? Even so basically in our domain, if you find, we have actually a lot of competitors doing actually in prod, and the problem is it's almost useless or even it's hurting, because the issue is that if I find bug in your code, yes, Google most of the code they can fix, but even Google, the safety critical code is very hard to fix. So if you find it during prod, it's unless you have an automatic way to fix it, which people are trying in different things, and including us. But the issue, you understand, it's too late. It's too late. You even prefer.
You can well imagine that I went into these in-prod analysis companies, and I said, You're trying to bolt the door, or to close the door after the horse is bolted, right? And so now I'm bringing the static, the earlier. So I agree with you, but I'm not going to then say don't do the in-prod, because it does have all the advantages that I've listed. So it's very important not to take one extra advantage and then to get rid of all those ones.
No, but all I'm saying, maybe there is, I don't know, there's some rule that says that the preservation, at least in Hebrew, preservation of difficulty, that maybe you should go in the middle. Maybe you should even don't abandon the testing thing, because
I'm not abandoning. Listen, I want to ship testing to 1,000 companies, but I just don't know how to do it. Right?
Yeah.
And if you figure out how to do it, that's an entirely new unicorn startup.
Please.
At some point you said, so first of all you said that he forgot the name of the tool, the taint tracing one.
Socolan.
It would run in 30 minutes.
Yeah.
On what machine? Because you're at Facebook, so
well,
you know.
But still, it's 30 minutes for over 100 million lines of code in the data centers. running in the data
So,
centers.
normal Facebook servers.
Okay,
It's the same servers you run Facebook on, Instagram on.
fair enough. And the other question is,
Francesco?
We can discuss it. So the particular number is one server. We have distributed architecture. We also did it for simple functions. Distributed it for other reasons.
thank you. And the other question,
By the way, thank you for the question. This is just a general comment. Think of me as someone coming from industry. What we missed so far that we are forgetting here, or actually Peter talk, that is very, very, very important to scale those analyses.
Yeah.
So if you think it's extremely important to make them run on distributed environment. So if you think how Google works, how Azure works, how Facebook works, how Amazon works, they work because they are massive distributed systems. When I see static analysis, they always think about the single thread, uniprocessor, and how much memory. So if I could do my desiderata, would be make your analysis distributed. Think about distributed analysis. Sorry.
no, that was interesting. And the other question is, you said it's internet facing, and you can only know that because of dynamic analysis. Static analysis can do that.
Yeah.
Why is that?
Well, because it's internet facing, because it's been deployed to a machine which is connected to the internet. So if you just look at the repo, you don't know that.
Okay. I get it.
So the fixed rate, the 70% fixed rate,
Yeah.
that it's true you can measure it, but I'm wondering, is it all really true positives, or maybe,
They could be fixing false.
yeah, people willing to take something that's just a false positive, but they're happier because now they don't get this red flag on your build
Well, that's
system,
what
on your CI
It
system?
might be. Remember, I gave you the story where we sent a taint analysis warning to the Googlers and they just fixed it. That might have been a false positive. Nobody knows even now. So, but that's the story of types too. With types, you're fixing loads of false positives all the time, but in aggregate, you get a gain for that. But it might be. But I can measure it. It is giving signal. Do people care? Whereas false positive rate isn't giving that signal.
Yeah.
Uh-oh.
No, I just wanted to go a bit further and say it might be even good to report some false positives sometimes because they might make the code better. Like if your static analysis is more regular and more predictable and teaches engineers to write better code, then that might be at the cost of some false positives. But overall, if the tool can understand it, then that means the code, and a human can understand the code as well.
Plus one, I agree. In general, you think that if the tool is written well enough and it can't understand some code pattern, probably your code pattern is bad.
Maybe I'm being too cynical, but the incentives, there is a way for the incentive to be
No, they are not evaluating.
You report 100
It's true.
bugs, the programming team say, I fixed 100 bugs, none of them are really bugs, but everyone is happy. I'm not saying that's what you have. But,
They can completely ignore the bugs and everything is fine.
They're not paid.
They are not yet. They did not change their evaluation. They do what is best for their code. So that's
Where the incentive comes is if they ignore the warning and then it crashes later, or there's a big problem later, then somebody will say, well, why did you ignore the warning? But yeah.
And the other thing is also the ethics. You have to think that those are professional programmers.
Yeah.
They really care a lot about the code quality.
Yeah.
So when you give them a message and they say something can be wrong, they really care about it because it's also the reviewer who look at the code. So this is also, I guess, goes what Peter was saying, is also who is the target. Those are professional programmers. They really care about code quality.
Okay. So I have a very naive question to ask.
Yes.
About so you displayed some scenarios that you get from dynamics analysis that can be used to explain the false alarms or in preventions. I was just wondering how simple they are. Are they simple enough to be understood by reviewers? Or?
Which ones were we talking about? These graphs I showed?
Yeah, these graphs.
I'm sorry. The graphs. The target of the graphs is the security engineer, the security expert, and so the way the security expert works is. You say to them, oh my God, we've got this system. Where are the risks? I need to control the risks. And then they say, where are the assets? Where are the databases? Where are the machines? And then they say, where are the known vulnerabilities? So then they start exploring the graph, trying to get a global picture of where all of the problems are. It's like if you have to secure your brother's house, the first thing you do is say, where are the windows, right? Oh, are there locks on the windows? So first they do reconnaissance and they think about all of that. And so the graph totally helps them with that. And so the dynamic analysis is maybe like some camera that went into the house and it found all of the windows and things like that without knowing the blueprint.
So is it a big object or is it something simple?
It's huge, but
It's huge, yes.
It's massive, but you can take views of it.
Okay.
Right? So
You have ways to explore it and to zoom in
it's
out.
abstracted. Like it may be that there's 15,000 windows, or there's 15,000 hosts of some similar characteristics, so they'll be put into one node. But the graphs can be very big, and so you end up saying things like, here's a target. Here's maybe a database. Now I want to understand things going into that database. We might look at the paths going into that database instead of having to explore the whole thing. But yeah, it's big, yeah.
Okay,
Yeah.
thank you.
Okay.
Let's thank Peter again.